We're going to wrap up Chapter 17 and the semester talking about explosives, which are similar to fires and accelerant analysis, but a little bit different chemically and also in how they behave. So these are substances that undergo, it's still a chemical reaction like combustion, but it happens, in these cases, they produce a large amount of gas. So there was no gas, all of a sudden you have a lot of gas especially. So now that gas has to go somewhere, and sometimes that can create this explosion. That sudden buildup of gas pressure is what makes it an explosion. Depending on how quickly it builds up and whether it's in a container or not in a container, we're going to classify different kinds of explosives based off of that. Okay, so we begin talking about low explosives. Low explosives have to be in a container because they're not going to build up that gas pressure as quickly as a high explosive. So we have a couple of examples. So black powder, and that's kind of, like gunpowder. It's a version of gunpowder. And those have nitrates in them. And then we talk about smokeless powder, which is nitrocellulose, nitroglycerin. So these are good examples of low explosives. So we put them in a pipe or a container, might be might even be a Molotov cocktail. So it's enclosed in a container. And it takes a while for that decomposition of the explosive to happen, and it builds up and builds up and builds up pressure. So because it's a little bit slower, we call it deflagration. So the rate at which it builds up is called deflagration. And we will use a different term when we're talking about high explosives. So that rate is going to determine how strong it is and how quickly it's able to build up and then break the walls of the container and explode out. These are the ones that tend to have, we're going to have shrapnel associated with it because they're enclosed in a container. On the other hand, we have high explosives. High explosives, there are two different types, but these are not going to be required to be in a container. So primary explosives are very sensitive, sensitive to heat, sensitive to shock, being hit, friction, so the slightest thing will set them off. They're not quite as powerful, but they're perfect for setting off the other type, which is called secondary explosives. Secondary explosives will produce gases very quickly, so they don't need to be in a container. However, they must be set off by a primary explosive or some other kind of triggered. So they're not sensitive to heat or shock. So you can hit them, you can warm them up, and they're not going to go off. Whereas the primary explosives are the one that go off super simply. If you compare a primary explosive and a secondary explosive, the primary explosive gets set off, which then sets off the secondary explosive. This should sound pretty familiar because in guns we had that. We had a primary high explosive in the primer that's real sensitive to that shock. So when the gun hits it, that can't remember the name of it, but that the firing pin hits it, and that sets off that primer, and then the primer sets off the gunpowder. Okay, so in this is going to a variety of different ones. Some are commercial ones, some have been around for a long time, and then some are military grade. So we have dynamite, TNT, those have been around for a while, and then these PETN and RDX are some examples of some more newer military and commercial grade ones. Again, as I repeat, the secondary explosives, which is one of the two types of high explosives, are going to need to be set off by a primary explosive. And the speed of how quickly it decomposes and builds up that gas is now not called deflagration. That's only used for low explosives. It's called detonation. There's some details about, because it doesn't need to be anything, because it builds up quickly enough that it can go faster than the speed of sound, and that means it can create a shock wave. So it doesn't need the container walls to press out. Instead, it can create a shock wave, which then carries that blast. So there's a slightly different detail to its mechanism. I want you to know that low explosives we're going to use the term deflagration to talk about how quickly they go off. And for high explosives, we're going to use the term detonation. So the we don't use a lot of nitroglycerin-based dynamite anymore. Remember, nitroglycerin was the low explosive. Instead, now most of these are going to be based off ammonium nitrate explosions, which is also used as a fertilizer. So this is certainly purchasing fertilizers in large quantities is often a trigger for ATF to be monitoring that person to see if they're looking to make explosives. And then we have our military peroxide explosives. Most of these are in the high explosives category. So RDX is one possibility. And of course, these are things that are monitored because they are powerful and can be small. There are definitely possibilities of being used by terrorists. RDX is very popular. One version of RDX is what you probably heard called C4, which looks like a putty. It looks kind of like a little bit like Play-Doh, gray Play-Doh. And so that is one form of RDX. And then we have one called TATP. This is triacetone triperoxide. TATP is fine by me. It is a liquid form, and it's that acetone and a lot of the acids are in liquid form, and then it's combined with peroxide. That's how it's produced. But because it is a liquid form, this is the one that has been used and carried on board on airplanes in terrorist attacks, and now this is why there's the rule about you can't carry more than 3 ounces of a fluid on as a carry-on. This is what they're looking for when they're going through all the security, is often looking for liquid explosives like TATP. Okay, so what do we do when we've had an explosion? How do we collect the evidence? How is that different from fires? So again, we are trying to search this now destroyed site in a similar way to how we had to search a destroyed fire site, but we are trying to go back to where the source of the explosion was. We're looking for, was there some kind of detonating mechanism for a high explosive? So it might have been, there's probably something had to set off that primary, and it might have been some kind of signal, it might have been a hit, a shock, friction, it might have been a heat source. So looking to see, can we find that? A lot of times in these detonating mechanisms often get left behind in some cases, whereas like with a match in fires, it tends to just be gone. Looking, again, for other objects at that site of explosion that might give us a hint to what kind of explosive it was and how it was created. You'll tend to get a crater, especially if it was on the ground or low to the ground. That initial shock wave and that initial blast often creates a little crater, and that can be very helpful for determining where the origin site is. Also, that loose soil may have remnants of these chemical remnants in them that can help us identify the explosive. So that's what we're going to preserve. We would preserve it in a way similar to how we preserve it for fire evidence. Another option that we have is using something called an ion mobility spectrometer. So this is looking for traces chemically of explosives. It works a little bit like, kind of like a JC, but a little bit different. The idea is that it still takes in a sample, it's going to ionize it, and then it can separate. So it's still a separation technique. And then as they hit the detector at different times, they're floating down this chamber, they hit a detector at different times, we can determine what it was about them and determine which one it was. It's kind of a specialty thing, but I want you to know they separate out and then detect different kinds of common explosives. I'm fairly sure these are the ones that they use on airplanes. If you get the random check and they take a swab on a little, like, looks like a little swab of cotton, and then they put it in a machine, I'm pretty sure it's an ion mobility spectrometer. So these can be used to detect in a fairly field type of application, can be used to detect traces of explosives. So we're going to examine, find these debris, find the detonating mechanism, find dirt near that crater site, collect it, and we can do chemical analysis on it. In these cases, often these are more complex molecules than accelerants in fire. And so there's often quite a bit of stuff left behind that can be chemically analyzed, so we don't lose it quite as much. We still are going to use sealing in airtight containers, it looks like a paint can. It was never used for paint. So we'd same idea, a little less worried about keeping a good headspace because probably these are less volatile, but still would keep a headspace. So you'd fill it about halfway up with the debris that you're looking for, different debris from different sites. We would still want to collect different substrates, so one from where the bomb went off, one from another area, to be able to do some comparison. And then that would be sent to the lab. Plastic is a no-no. Even if it's airtight, which is a good thing, a lot of these explosives can react with the material in the plastic and then escape through, essentially melt the plastic and escape through it. So it would be glass or metal. The standard is typically the metal paint containers. Once you go back to the lab, again, we have a couple of methods. So there's that ion mobility spectrometer that could be used as a screening device. And then that debris would probably be rinsed down. So they're trying to clean it up a little bit and get a sample out of it. And then probably would use infrared spectrometry. These are going to be much more complex molecules where infrared spectrometry can help me determine the differences. GC just gives me doesn't give me quite as much information. And in accelerants, a lot of the infrared spectrometry would be too similar, but for explosives, they're going to be very different. So the confirmation would be probably infrared spectrometry. However, gas chromatography and mass spectrometry might be used as sort of like a screening process to kind of get some information. Spot tests would be screens. So we're going to say the screens would be ion mobility spectrometer. The screening tests would be color tests. I'm going to show you in a minute. And possibly thin layer chromatography and GCMS. The confirmation is going to be an infrared analysis. Okay, so these are these color spot tests. So these are things that can be done fairly in the field. They're not quite field tests, but ones to try to determine which type of explosive it might be. So here's a variety of different common explosives. We see our PETN, our RDX, our TNT. Here's some nitrates we see them a lot in guns, gunpowder. Nitrocellulose, nitroglycerin, chlorate is another one. And there are 3 different tests. You may remember we vaguely talked a little bit about the Grice test in the ballistics chapter as being one way you can test for gunshot, is if it's gunshot residue. It tests for the presence of nitrates. It's not a fantastic test. It's more of a screening test. Notice that you can get either no color or pink red. So some of that is going to have, so you'd probably need to use all 3 of these tests and look for a combination to try to nail down what it might be. Another test is called a diphenylamine test. And for these, you can get either no color, which would be particularly helpful for TNT, is this is not one of these other ones. Or you could get a blue, black. Nitrocellulose gets you a little more black on this. So we're looking for blue is suggesting that you might have one of these. Alcoholic potassium hydroxide, KOH, is one that can kind of really help with the tetryl and TNT because you get a red-violet color off of those. The other ones would have no color. So be familiar with these tests. Know the different the names of the tests, the different colors that might indicate whether it's a positive or negative test. Also, when these are done, generally these are going to be washed with acetone, except if it's ammonium nitrate, we don't want to use acetone. So these are just some details of the specifics of the analysis.